Hey everybody, how are we doing? Josephine says, can we go over Canvas Content number 10? You bet. And Chloe says, I'm working on project 2. What does it mean by a categorical variable with 2 levels for the pie? Does it have a pie or bar chart? Does it do that? Where did it say? Let me double check. Because I didn't do that in my videos. Oh, I know what you're talking about. Oh, got to log in here. Got everything reset. Updating computer. Someone said, Wilson said about, oh, people are being so nice in the chat right now. People are talking about the class on YouTube and stuff. And like what I use is like, I use so many different things. So if Wilson's watching right now, hey, Houston, good to see you. Can we go over chapter 17? You bet. We got so many good things. Josephine, so good to see you right here. I've got so many different things that I use like at one time to do my streaming. So what I use is like I use a Stream Deck right here with all the different options and the integration so I can do all my different transitions. I've got you're going to see the world inside the world right now. So then I've got OBS over here. So here's the world inside the world with all the different things. So these are all the different things I've set up right here. So this is the world inside the world of what I do right here. So Wilson's watching. I was looking over at the Discord for a second. So this is the OBS studio that I use here, Wilson. So what happened is for some reason, my buttons weren't connected. So I've set up my Stream Deck. So you can see the Stream Deck right there. So I've set up the Stream Deck so I can quickly change like source inputs and everything. I need to reset this to the right screen. So I can easily turn things on or off. I can switch scenes. I can play music whenever I want. And all this is here on the Stream Deck. And I thought Ford. So yeah, I got a complicated relationship with technology. Luckily, the worst thing is the buffering issues. I really hate buffering. So we got one internet provider here, so we got to work with what we got. We work with that, and then I've got my even my keyboard is like a specialized fancy glowy keyboard. All that fun stuff right here. All right, we'll get serious right here. We'll get serious. Yes, the 2-level categorical variable. Let me go look at that real quick. Let me pull up Jump 16. This is a pretty quick one right here, so I'm going to cover it. And then we're going to hop over here and do some Canvas content. I'd say I love technology. I've been using technology for a long time, but my technology doesn't like me sometimes. Yeah, the whole thing just broke today with the tablet I used wasn't allowing me to write on it, so I just reset the computer. Number one way to do it, reset the computer. Oh yeah, let's go look at a 2-level categorical variable, Chloe. We're going to take a look at a bar or pie chart. Let's go check out a look at this. So when we talk about a pie or bar chart, I'm gonna fix the extra credit thing between the scenes right here. Bar charts can only be made for what variables? Pies or bar charts can only be made for what variables? Pies or bar charts can only be made for what variables? So pies or bar charts, you can see there in the top right corner, pies or bar charts can only be made for what variables? Categorical, Chloe, 100 points in the chat right here. You are right, categorical. So how can you tell if something's categorical? What color will it be in jump if it's categorical? What color will it be in jump if it's categorical? Great job, Josephine, also. Let's go here to not top chat, but live chat. Great job, Houston, right there. What color will it be in jump if it's categorical? Categorical variables in jump are what color over here on the side? What colors are they? Who knows what colors they are? Categorical variables will be what colors? Then we'll do some Canvas content after this. Categoricals will be what color? Do you see it? We got Broken a Bone. Now, Broken a Bone is a 2-level categorical. So these are the people who have not broken. These are actually bar charts right here. Don't take a picture of that. But these are actually bar charts right here. Red, Chloe, great job following along. They're red, so you can see right here longest or what relationship are you in? You're born in Tennessee. So that's a 2-level categorical right here. So what does it mean that it's 2-level? A variable type like categorical versus quantitative. Great job, Houston, there also. Then we have inside of categorical variables, levels. So levels just means answers to a question. Just give me a number here like Q16. That would not be a right answer. But do you see another one that's a 2-level categorical variable? Now it needs to be red, which means it's categorical. But do you see another 2-level categorical variable on the screen? Just give me the number like 14, but I'd say nope. 14 has a ridiculous amount of levels. You can see right there, there's tons of levels to it. Do you see another 2-level categorical variable right here with the data set I have that you could like use if this was your data to analyze a 2-level categorical variable? Which of these is a 2-level, which means 2 answers to the question where we put people into categories. So we mean by 2 levels. Honors, number 17. Are you honors? Are we not honors? Great job, Chloe, right there. You're right. So we're going to go to Analyze Distribution. So I'm going to walk through the steps on this real quick. This is the first question right here, and on the project outside the executive summary. So we go right here to Analyze Distribution, and then we double click Q17 Honors Program. Great job. Q19 Student Loans. Do you have student loans? Do you not have? Houston, excellent work. And so we're going to analyze this one right here and click OK. Analyze Distribution. So now we have our distribution. I don't think this one says add the count axis to it, but we're going to do a little extra right here, a little Salt Bae extra right there. So we go here to the top right arrow, and we'll zoom in. We got all the things back here. And then we go to stack right here. And so with this, we can see the distribution stacked. So we get a whole extra point for being the... you can get up to half an extra point for conversing on Discord. And thank you. I saw a bunch of people just chatting away on Discord. I love it. So we have here analyze distribution. you have to converse every once in a while on Discord, and you get points like for conversing every once in a while. Then we're going to go here to the here. I'm going to bring it back a little bit so you can see what I'm showing. You click right here, and you can go to histogram options. These are the accoutrements. Count axis, you don't need that, but it's nice. You can increase the font. We're just making our picture look nice and neat right here. Got to make your graphics look pretty. I'm going to go over here to histogram options and go to, oh, you can't see it. I hate that. It's right there. Histogram options, and I'm going to go to, where's my color? I'm going to go here to a nice blue today. There we go, nice blue color. And there we are. We've got here how many people are in the honors program, how many people are not in the honors program. Easy 0.5 points. You bet right there. Easy points. No classes over. Complicated relationship with technology. And so we click here to the red arrow. At the red arrow, we're going to go to confidence interval. And I'm a 95% confidence interval type person right here. And so what is this going to try to estimate for us? Well, if we have a sample of 806 students, we want to estimate the true proportion of students who are in the honors program. So I am 95% confident the true proportion, like for all students, the true proportion of students at UT who are in the honors program is somewhere contained in the interval 9.15 through 9.513% to 13.9288%. So I'm 95% confident the true proportion of students who are in the honors program at UT is contained in the interval 9.513 to 13.9288. With 95% confidence, I think the truth is in that interval. And you could do it for the no, all that good stuff right here. But this is how many students we saw in our sample, 93. And this is the proportion, because you notice here it adds up to 100% out of 1, 0 to 1 being decimals. So does this make sense right here, Chloe, on what you'll be analyzing? This is more of a quicker version of me talking about it and showing the output for this question, trying to make sure we understand we're analyzing a categorical variable here, trying to make a confidence interval estimate what is the truth for it. Like in our sample, we saw 11.5% of students in the honors program. Oh no. That's interesting. I'll have to look at mine too, Marjorie. That's interesting. Actually, I think I noticed that. I have Google Outlook too. Oh, that's an Apple thing, right? I don't know. I use my Google for my alerts on my phone to get like class alerts and stuff to tell me when class is coming up. It's really nice. It's really nice. If you, Marjorie and Chloe might confirm this, but life advice right here, if you start using like Google Calendars and you put everything in your calendar, you get so much more organized and you remember everything so much better. I mean, who would think reminders with all the technology we have is a great way to do things. Back when I was a kid, we used to have that book where you had to write everything down and be like, here's my planner for the week. No, now you just put it all in your calendar and you can set a recurrent event, but it's a huge thing. So hopefully Marjorie fixed that right there. So Chloe, if you have questions, let me know. We're going to hop and do some Canvas contour error. Yes. When it actually alerts you, it's so nice. Great way to stay organized right there. Awesome stuff. Great work, everybody. Got everything fixed up right here. My Apple Calendar has failed me this semester. No, Sophia, no. You know what will not fail you? Canvas content number 10, the last Canvas content of the semester. Let's do 2 versions of it. Let's knock out these Canvas contents right here and do 2 versions as we fight technology. I love seeing, oh, thank you. What's Wilson saying? Oh, thank you. Thank you. Thank you, Wilson. Thank you so much. I try to read everything. Some people are, like, yeah, no, I love it. And you're like, oh, someone just got their 5 points. Someone just got to level 5. Oh, You guys are just being too positive. You're so nice. You can't be too positive. I like it. No, I really want there to be a good community, but if you look on the Discord in the chat, someone just got to their level 5, so that's 0.5 points on their final. Does the project have to be turned in on Friday at midnight? Yes, that is correct. My canvas is linked. Oh, man. Yeah, it's nice to get those alerts. Can we do chapter 17, the computer software? You bet. On the canvas content. Yeah, let's try to do that. Let's try to find that one. We'll find that one, Michael. That's got it. Oh, you're too nice. You embarrassed me. I really appreciate that. I want people to have a really, you know what? I just think about it like this class is something you get to experience. And to me, I want you to have a good time in this class, build a community, get to know each other, and remember this class. If you ask me how many classes do I remember from college, a handful. I hope this is a class you remember. I hope you remember the material. I hope you remember the experience. I hope it makes your life better in some way. Let's hop back in here. Let's do some Canvas content. Number 10. That's one of the versions we already did. Let's do a new one. Here we go. Let's make the font bigger so you can actually read it. The results of a chi-square test for independence conclude color choice is dependent on the gender of a kindergartner. Which of the following is true? Great job, Kayla. Now, Kayla knows the null hypothesis for the chi-squared, and you ready for this? It might be EpicPen that's breaking it. So let's bring up some copy-paste. We're going to go back to copy-paste because I had a weird issue yesterday, and then we crashed. But guess what? And Microsoft Word updated. Oh, it looks, don't got that blue top. I missed that. So now we look at this right here. When we do the chi-squared test of independence, which we'll be talking about next class, what kinds of variables are we analyzing? When we do the chi-squared test of independence, what kind of variables are we analyzing? When is this due? Because it can't be due. When are we doing, what kind of variables are we analyzing when we do the chi-squared test of independence? What kind of variables are we analyzing? Two categoricals. Because what will we get right here with the chi-squared test of independence? What will we get? By analyzing two categorical variables, the 29th, perfect. Marjorie, 100 points. Thank you for answering that question for me. More than enough time. We're good on it. I was like, is it due like this week? Because if it is, we need to extend it. What will we get graphically? I need to disappear. Hint, hint. What will we get? Contingency. Exactly. A contingency table is great for it. And we'll also get a what, which is what I drew on the screen right here. We'll also get a what. We will get a contingency table, which I didn't draw, but we'll also get a what. So contingency table, look at what I'm blocking right now. We'll get a contingency table and a what else. The thing I drew on the screen right there is a mosaic plot. So you would look right here and you'd say, oh, if we're on different levels of X, the level of Y looks to be different right here. And we can make a pretty quick mosaic plot right here. We can go over here to analyze distribution fit Y by X. We could see if somebody's gender plays a role in whether they've broken a bone. And what would you say to me about males and breaking a bone right here? Just looking at this visually, what do you notice about males and breaking a bone? And let's talk about the null here for a second on this, because it's really easy to remember the null hypothesis, and then we'll go look at our question. What would you notice about males and breaking a bone? Doesn't mean all males have broken a bone. Doesn't mean females don't always break bones. But what do you notice about males and breaking a bone right here? Switch it. So males, 54.65% of males have broken a bone compared to, for females, 40.13% of females have broken a bone. They are more likely to break a bone. We might not say on average. Marjorie, great answer right there. That might sound like quantitative. We could say knowing that somebody is male would give us information that they're more likely to break a bone. Like, I was about to say on average too. Another 100 points. No, males are more likely to break bones than females. It doesn't mean you will break a bone if you're male. It doesn't mean you won't if you're female. There's a lot of males who have not broken a bone. There's a lot of females who have broken a bone. Exactly. Males are more likely to break a bone. And the differences we observe are unlikely by random chance via the p-value. Remember this? The Pearson has your p-value. The Pearson has your p-value. So the Pearson here shows us that we reject the null hypothesis. And what is the null hypothesis? That gender is what to breaking a bone. And this is really easy to remember if you know this is the chi-square test of independence. Gender is what... Nice job, Wilson. Gender is what to breaking a bone. Gender is what to breaking a bone. Gender is what? Independent. That's all you say. Gender is independent of breaking a bone. That means it would tell you nothing. Like, I know somebody is male. That tells me nothing. But we reject that and we say we have evidence that they are not independent. We have evidence of association. Let me just throw some awesome level 5s in the chat. Wilson, you're crushing me. Oh man, people doing the rank check. People going crazy on the rank check over here, looking at the ranks. Wilson's got their rank. Great job, love it, love it. And people over here in the general chat just having a good time. Pause are in the chat everywhere right there. Pause are in the chat. So great job, everyone. And you can hang out. You can still remain in the Discord later on after you leave the class. You can talk to 201 students. You can general chat, all that good stuff. If you take a 320 course, you can go there too. Let's go look at the question. Someone's like, what about the question? Let's go with the question. The results of the chi-square test for independence conclude color choice is dependent. So what did it sound like we did? What did it sound like we did if we conclude that they are dependent? Remember, the null is that they're independent. So if we conclude that they're dependent, A, B, C, or D. Because the null is that they're independent. So what does it sound like we did right here? A, B, C, or D? If we rejected the null, and rejecting the null, I can now write on the screen again, sounds a lot like low p-value. So you're saying you have evidence for the dependency, so we reject the null. You got it right there. Great job. We rejected the null. We have evidence, so the p-value is low because the alternative is that they're dependent, so we have evidence for the alternative. So great job right there. The chi-squared test is used for testing hypotheses of the association between two categorical variables, true or false. Here, I'll give you a hint again. Chi-squared is used for two categorical variables. Chi-squared is when we draw that mosaic plot or contingency table. So look at my graphic right here and see where they intersect. Can't do it. Just look at that and that. What I'm covering up right here. Chi-squared is when we do mosaic plot and contingency table. So is that two categorical variables? We just did some examples a moment ago with breaking a bone and gender. So chi-squareds are used for two categorical variables. Chi-squared test of independence. What do you think? Did your daughter sneeze you? True or false right here? Who's got this? This is the test. You're like, oh man, I need this question to make an A. Very true right here. You got to kill 100 points in the chat. So there we go. A contingency table is a key component in understanding the chi-square test of independence. Well, let's go look at our output. Do you see contingency table right here and a chi-squared test of independence? I mean, we don't see the... Now we do. What do you think right here? Where is Mubot? He's breaking the world. We need to throw out the points here in a second. Sorry about that. Mubot's waking up. He's waking up. That's what Mubot actually looks like, but there's his form over there. So is a contingency table part of the... I reached the computer, forgot to mute. I'm sorry, Mubot. Sorry, man.
I am Mubot.
He's not happy about that. Do we use a contingency table with the chi-squared? Yeah, the Mew on his helmet? Yeah. It's commissioned artwork. So I commissioned the artwork. When did I do it? I think in December I did it. Commissioned the artwork from a person who does like all these different anime drawing type things. So that's our own artwork. So we can't get copyright claimed on it until I find out that they stole it. And I'm like, but it's our own commissioned artwork. Mubot right there. He's my little dude. So what do you think? Contingency table, chi-squared. I see chi-squared. I see contingency table. What do you think? True or false? What do you think? True or false? Oh no, maybe we're trying to trick you because I see a contingency table and I see the chi-square test of independence. Very true. Very, very true. Let's throw some 500 points for everyone who's here. Points add plus viewers. 500. There we go. Points in the chat. Mubot's trying to alert me to something. Chill out, Mubot. There we go. The next one wants us to find the T ratio. So the T ratio is a complicated equation, which is the difference divided by the standard error. Oh, we don't have the notes up from today. So to do the T equation, the mathematics are... I do not like that new blue background. No blue background. Y bar 1 minus Y bar 2 over square root S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. So this right here is the T ratio. Kayla's already got it for us. This is when you do a 2-sample t-test. And the top of the equation is known as the what? What is the top of this equation known as? Like, just tell me that's a what? Between those two means, that's just a what. Look at it. You're subtracting two things right here. That's just a what. The top of this is just known as a what. Just a difference right here. That's all that is. That's a difference between the two means. Just subtracting two sample means. And then the bottom is known as a what. It's kind of like s over square root of n. The bottom of the equation is a what right here. The bottom of the equation is a what. We use a little more advanced notation on it, like SE sub something something. It's just the what of the difference. You can tell me in the two-letter notation. Yep, standard error. So that's going to standardize it. So if you know that this is the difference divided by the standard error, take a look at the output. What do you notice about this output? Here's the difference. Here's the standard error. So Kayla, who'll put it on the screen at the same time. Kayla, do you want to write the equation, get another 100 points for everybody? Like, what are you going to do if you have the difference and you have the standard error? So this is the difference between the two sample means. That's what that is mathematically right here. That is the difference. Like, we observe a difference between the two means. Like, we have group 1, group 2. They have a difference of 497.3. The standard error, which is in Houston, great job there also. Everybody 100 points. Keep it up. So what do? Kayla just put it in the chat right there. Kayla showed it mathematically. I'll show it on the screen. Thank you so much. We just take the difference of 497.3 divide by the standard error of 4.8, and there's the t statistic right there. We got it. That's the t ratio, which is the t statistic. It's what it's called in the output, difference divided by the standard error. 2 decimal places and round up. If you ever get anything wrong by a tiny bit, tell me, because I'll make an error too. You never know. Below is a jump confidence interval for the difference between the two means. What is the corresponding level of significance to the confidence interval? Okay, cool. When we build a, really? Tell me, what kind of confidence interval did they build? Because they're being weird. Being wacky. What kind of confidence interval did they build? Wacky Wednesdays. What kind of confidence interval did they build? A 91.6% confidence interval. So whenever you want to talk about the corresponding two-tailed test, great job, Marjorie and Kayla, the corresponding two-tailed test and a confidence interval will always have a corresponding two-tailed test, because a confidence interval looks like this, and we're talking about the inside, and we're talking about shading 91.6%. And the two-tailed test is going to be the corresponding outside, because the two-tailed test is the outside. Total weirdos. It's okay. Who wants to be normal? Only this wants to be normal. Stats jokes. But if I had just had it queued up, that's totally. There we go. Looking good. What is the area shaded on the outside for the corresponding two-tailed test? And I think once it has a decimal, what is the corresponding outside area? I don't use the sound effects much because I have to be like, where's that sound effect I'm looking for? It was bad. It was a bad joke. 8.4. And I think it wants it as an alpha. Let's double check. And that's just the outside right there. It wants it as a decimal. Please tell me if, and all we did was subtract. These are complements of each other. So confidence interval and corresponding two-tailed tests are complements. This is kind of a review. This is why topics kind of build. But the corresponding, great job, Marjorie and Kayla right there, the corresponding two-tailed, and this would be a decimal. So let's put the answer up here as the following right there. So it's 8.4% on the outside, but the corresponding alpha, sometimes people say 5% alpha, but usually here 0.05 alpha. Like, this is a 0.084 alpha. It's fine. What? We're done? Yeah. Let's do another version right here, see what we get. This is really good practice for the test because, cool. This is really good practice for this. Oh, one of my favorite questions in the world right here. We have here the chi-squared test with the degrees of freedom. Now, the way to do this, these are one of my favorite questions, is to look at this and say, Brian, this is a what by what. I want you to be very careful and say, Brian, this is a what by what. Brian, I'm looking at a what by what grid right now. Be careful. You could be tricked. I want you to see the common error people make on an easy question about degrees of freedom for the chi-squared. This is degrees of freedom for the chi-squared. We've not covered it yet, but it's one of my favorite and quickest questions you can get right on a test. Brian, I am currently looking at a what by what, and it's the amount of levels you're looking at, like how many levels does gender have here, and how many levels does broken a bone have. People get tricked by looking at this, though. It still does have this. It's a 2 by 2. Now, be careful. Some people use the total. Don't do that. Here's what I'd like you to do. I wish this in in-person teaching, Marjorie, Josephine, everybody, great work. Yeah, I give it a quick scan, like a 30-second, try to catch any major issues. Usually I can make sure people get in the high 90s if they turned in early. So send it to me and I'll give a quick scan looking for major issues. Because if I give 1 minute, that'd be 12 hours to everybody. Like, yeah, spend whole days looking at projects. But I try to give a quick scan. So this is a 2 by 2, right? So now I'd like you to delete one finger on each hand and do the formula 1 times 1. So 2 by 2 is the formula 1 times 1. So how many degrees of freedom are there? Who can tell me the degrees of freedom for this chi-squared, which tells you which chi-squared you're using? Aloha, Diddle. Great to see you here. Great job yesterday. Everyone, great job. We had a fun class yesterday. There is going to be 1 degree of freedom. So Brian, or say to me, Brian, this is a what by what here. Now be careful. Be careful. Brian, this is a what by what right now. So look at this one and say, Brian, this is a what by what. Be careful. This is where an error occurs. It's funny. You could actually make the error and get it right. But if it asked you what are the degrees of freedom, you get it wrong. So Brian, this is a what by what right now. Remember, don't use the totals. I'm going to catch someone from making that error. Don't use the totals. Brian, this is a what by what currently. It's a 2. Wilson, great job. Another 100 points in the chat. It's a 2 by 5. It's a 2 by 5. Does it make sense here? There's 2 levels here. That's why it's 2. And 1, 2, 3, 4, 5. Don't count the totals. It's a 2 by 5. Does that make sense? There are 2 levels to the outcome, failed and success. That's 2 possible things right there. And then there's 5 up here. Don't use the totals. And then we don't use this either. Does that make sense? I'll take a look at it here a little bit later. Great job, Tiffany. So 2 rows, row 1, row 2, 1, 2, 3, 4, 5. Who's with me on that? Now, who can find the degrees of freedom? Who can tell me the degrees of freedom for 400 points? Let's just go crazy today. So many people practicing up right here. I love it. Who can tell me the degrees of freedom for 400 points? Who can tell me the degrees of freedom for 400 points? We do it in parts. I think Kayla said the 10th and the 15th. Kayla, double check your work. 400 points. Josephine's right. It's 4. Because if it's a 2 by 5, do you see it? 2 by 5, drop 1 finger down on each hand. Does this make sense what I'm doing right here? Who's following me right here? It's a 2 by 5. You're getting it. Wilson, you see it right there. You get it. Let's do an absolutely ridiculous one. Like, let's say I asked you to do a crazy thing right here. Let's not go too crazy because it's going to be a mess if I draw it. Let's do relationship and distance from campus. This needs to be the X. How many degrees of freedom will this have? Don't want to show the answer. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, cool. How many degrees of freedom does this have? You have to count it out like me. How many degrees of freedom would this test have right here? It probably has issues with, it's going to have issues. We'll ignore them for the moment. Because widowed is causing issues with expected cell counts. We'll talk about more. Kayla, 100 points. You got it. Yep. Wilson, you got it too. One of the easiest questions on the test are what are the degrees of freedom for this chi-squared test? You just say, okay, how many levels? 1, 2, 3, 4, 5, 5. 1, 2, 3, 4, 5. 5 by 5. Drop each down. 4 times 4 degrees of freedom. And you get that formula on the test. It's rows minus 1 times columns minus 1. And that is the version of the chi-squared we are using. One last thing I do want to mention right here is just like the T, the chi-squared has degrees of freedom. Yeah, it's like once you see it, like, oh, it's just 5 by 5, 4 times 4, 16 degrees of freedom. So the chi-squared uses degrees of freedom, and this makes the shape of the chi-squared. So MuBot's telling us where to go for our chi-squared. We would put 16 degrees of freedom in here, and as with the T curve, more degrees of freedom means a more normal distribution. So the more degrees of freedom it has, this one doesn't draw after so many things, but the more degrees of freedom it has, the more normal it is. This one has a right skew to begin with. But the degrees of freedom just tell you the shape of the chi-squared, like the degrees of freedom on the T just tell you the shape of the T, and the more degrees of freedom it has, the more normal. So when you have a chi-squared, you have to know what are the degrees of freedom to know the shape of it. Different degrees of freedom make different shapes for chi-squareds. So a little bit of review right there. So yeah, good review. Great stuff. We like reviewing the topics. Where'd our question go? Oh, it's over here. This is false. There were 4 degrees of freedom. It's a 5x2, drop it down. So yeah, 5x2 drops into 4 times 1. Not quite comprehensive, but material builds, and we have tools and techniques questions. The expected cell count is based on a researcher's opinion. The expected cell count, and we'll use one that's a little more easy to understand right here. With expected cell count, I want to show you a very, we'll copy paste it. I'm a little worried that EpicPen's causing problems on my computers. To get the expected cell count, 1, Rock, what about my opinion?
It doesn't matter.
Rock just answered our question right there. That's the answer to will my opinion dictate the expected cell count? No. Let's go find an expected cell count. You do formula 2. You're like, what do you not love, Brian? Everything. I love everything because everything is awesome. And everyone's brought me so much positivity today. A little bit of computer issues this morning, but so much positivity. So the formula for expected cell count is row total times column total over grand total. Row total times column total over grand total. It basically points in on the one you're solving for. So we would be solving right here for broken a bone no and female. So when you do this right here, this is the formula for an expected cell count. Like how many females would we expect by random chance to break a bone? So how will we know which formula to use? Yeah, that's a really good review question, Kayla, right there. We'll be doing a lot of review and like which problem to use and when. And I've got the review videos on those. That just comes with the practice. Like if we have 2 categorical variables, then these are the formulas we'll use. It really comes down to variable types. And so Kayla's solving it right there. Great job, Kayla, right there. Just solving this out. Just plug in your numbers right here, and you can literally write the equation by just circling the numbers. So what would this mathematically solve out to here? If I did 355 times 431 divide by 806. So if I did this mathematically, what will I get? And I'll show you. Jump does all the work for me if I really want to see the answers. I do 355 row total times column total. I have a grand total. And these are the amount of males I would expect to not break a bone. And I expect by random chance 189.833 males to not break a bone. And that's just the formula row total times column total over grand total. The last task on, yeah, you bet, definitely. We'll do that here. We'll do about, I think we have 2 more stats ones lined up. Then Cora will do some 474. Excellent question. I love doing some like future things. So 201 can see like, where does this all kind of lead to? So this is not based on the researcher's opinion. Do we use the chi-squared for 2 categorical variables? What do people think about this? Oh, we'd love it if you got that on the test, right? Do you think we use the chi-squared for 2 categorical variables? Here's the chi-squared test right here. Gender, broken a bone. What do you think right here? True or false? Do you think we use the chi-squared for 2 categorical variables? Thoughts on that? Does that look like 2 categorical variables? Yeah. Yeah. Chi-squared is for 2 categorical variables. You got it. So we're definitely doing the chi-squared test of independence. If you did this one a little bit quickly right here, please check the earlier portion of the video where we talked about how we solve this. I clicked R. We will need R soon here. Reset the computer. How do we solve out this one right here? How are we going to get the T ratio right here? Who can solve the mathematics? We did this one a little while ago, but how can we get the T ratio right here? The difference divided by the standard error, which you see right here in this output. Here's the difference, which mathematically is this. The 2 sample means subtract from each other, and the standard error is this formula, which is just the standard error of the difference right here on the bottom. So when you solve this out right here, we're just going to take, Of course. Yeah, no, thank you, Tiffany. That's what I usually do. I won't usually do it like live during office hours unless someone's like, you'd have to ask, like, can you like, and then I might, with, we got a lot of great questions today. So I might say, like we'll do it later. But no, thank you, Tiffany. 100 points, Tiffany. Thank you for all the communication right there. And I really want, I mean this as much as I can say it. I want everyone to make an A. Oh man, I want a semester to go by where I figure out a way that everyone gets an A, not by just giving A's, but I figure out some way to teach that I don't lose any students. That's what I feel like when a student has to drop the class. There's reasons to drop the class. Life happens, but sometimes people don't meet their own expectations, and that's where I feel like I lost a student, when a student doesn't make the grade they really wanted to make. So, but that happens sometimes because we sometimes just don't, things don't line up. Which of the following is not a requirement for a 2-sample t-test? Condition 1. That's a requirement. Random. Condition 2. What else is a requirement right here? What else is a requirement? Condition 2 is what? I love, they're almost in order. Actually, they are kind of in order. We got lucky this time. So condition 1, random. We randomly select the observations for the groups. Condition 2 is 10%. And then we pause and we get to condition 3, which we have to then look at what kind of data we're working with. We're working with quantitative data right here. And with quantitative data, we have to look at to see if it's nearly normal. And that's not on here though. So we do need that one. And then the fourth condition for testing a 2-sample T is independent means. We went over that today. So if you're in the afternoon class, you'll hear more about that. Meaning the only one is this, because this is for what kind of data, which T's are not. Mr. T is mean. You're doing drugs. We have right here the success failure condition is for what kind of data? Success failure condition is for this kind of data, which we're not doing with 2-sample t-test. Success failure condition is when you're testing, like, does someone own a dog? Did someone make an A on the test? Not their grade on the test. Success failure condition is for what kind of data? We'll submit our quiz. It's for categorical proportions. Exactly. Great job, Kayla, right there. So if you're doing proportions, you'll do some form of the success failure. We're getting those 10 out of 10s. You know how we roll right here. So let's hop back to the main screen. Great work, everybody. Let's see. I think we had a few more. We got a lot of questions lined up, I think. Okay. Can we go over the chapter 17 computer software question? Oh, what's this computer software? I don't, my brain can't think of it. Computer software, chapter 17. It's a quiz question, is it? Homework question. Oh, good. That's why I haven't thought of it and we haven't done it lately. Chapter 17. Thank you, Michael, for asking that question right there. This question goes out to Michael. And this reminds me of Stranger Things. We still have Stranger Things season 3. Don't tell me what happens. But I want to know that Superman appears in the season. Probably does. Who here has watched Shazam? You should check out the movie Shazam if you haven't, and wait. Just watch the whole movie. I don't want to like allude and someone figure things out from what I'm talking about, but watch the whole movie. Watch Shazam. I really like Shazam. I'm not a big fan of what DC makes. I mean, I like some DC stuff. Superman, Batman, all good. But Shazam, really great movie. So check out Shazam. Yeah, Kayla knows it's just some Shazam right there. The homework, awesome. Let's go check it out. But Shazam is such a good movie. Did you wait? No, it's not an end credit scene. It's the very end of the movie, I think. God, it's so good. Man moves to a new city. Which question? Well, I like DC. I just don't like their movies. Like, once Nolan stopped working on their movies. Oh, here we go. I got it. Found the question. All right. I mean, Marvel's just crushing it. You see that new Spider-Man preview last night? X-Men 97 is coming from the MCU's. Wait, so is that a new movie? They're doing like are they doing another X-Men reboot? Is it going to be like, because that's Marvel's X-Men. Is it? Yeah, Shazam is awesome. Like, I mean, it's just really good. Just Billy Babson and everything. It's just such a cool story. Let's go check out test scores, the traditional, non-traditional. Let's go check it out. Yeah, go check out the new Spider-Man trailer last night. Ooh, don't want to ruin anything. Go check it out. Looking good. Oh, that's all right, Michael. Yeah, I was like, which one is it? We got this right here. Yeah, it's gonna be super exciting. December. Gotta get that new Spider-Man game for my PS5. Yeah, know what I'm doing over break. Sale on it. Okay. What is the margin of error for this interval? So the margin of error is always what? Whoa, Sophie, you just blew my mind right there. Wow, that's amazing news. What is the margin of error? What is the margin of error? That's good stuff there too. What is the margin of error for this interval? Check out Wolverine and the X-Men. Check out Wolverine and the X-Men if you haven't checked that out, Sophie. Check out Wolverine and the X-Men. You should watch that. That one's a really good series. There's a lot of really good stuff. Wolverine and the X-Men was really good. Upper minus lower divided by 2. Michael, great job. Michael just put in the chat, upper minus lower divided by 2, which is half the length of the interval. Let's show the equation Michael just mentioned. I'm going to try to focus. Upper minus lower divided by 2. Now, what we've done right here mathematically is we find out how far these two numbers are apart, which is the distance, and then we divide it by 2. So you're literally figuring out the distance between two numbers, like -2 to 4, and be very careful. What would the margin of error of this interval be? Now, this is not our interval exactly, but just I want you to think mechanically, how far away are these numbers from each other? And then divide that distance in half. Just tell me, what do you think? 100 points right here. What is the margin of error of an interval that goes from -2 to 4? If you just look at this and helps understand the concept, you can do the mathematics if you want, but just think, what is the margin of error? I've drawn it there visually for you. The margin of error is plus or minus what on this interval? So what would it be? It helps to not just know the formula, but to see what the formula is doing. It's half the length of the interval. The top part of the equation is the interval length, and then dividing by 2 is half the length of the interval. So the margin of error is always half the length of the interval. And so what would this mathematics be for what the margin of error is? 100 points in the chat. Who knows? Then we're going to solve ours right here. What would that be mathematically? 3. Kayla, you got it right there. It's 3. Yep, because it's +3 -3, and the center of the interval is 1. So the interval could be written as 1 plus or minus 3. And then just double check your work. If 1 plus or minus 3 turns into the numbers -2, which it does, and +4, you solved it out properly. So we've done it. So all we're doing is the formula upper minus lower divided by 2. So let's go back and run that. Upper minus lower divided by 2. So good formula to remember for confidence intervals, margin of error. Upper minus lower. Now it's a minus minus. So when we minus the lower, we're actually adding it, because a minus minus is adding, because when we do upper minus minus. And so they're about 6 away. There we go. Very similar to what we just did. And if you look, that looks about right. Oh, really? I guess it would be right. Let me double check. 2.299 plus. Yeah, there was a decimal error. Oh, when you divide by 2, it is that. So type in an integer or decimal rounded to 3 decimals. Gotta love those very exact decimals, right? Check answer. Woohoo! If the 95% confidence interval was created, would this be larger or smaller? So we're at 99. Thank you, Kayla. Double check. 100 points. I appreciate it. Clicked the button by accident. If we're at 99 and we go to 95, what would happen? Because we're at 99 and we go to 95. So what happens to the interval? We're at 99. And if a 95% interval had been created, what would happen? And I'll show it here visually. If we went, it'd be smaller, exactly. And you have to think about the area covered on the curve. I think we might still have up a t interval. We have it up over here. So the t distribution, if we are on a t and we cover the middle 99%, or we cover the middle 95, it gets smaller, or middle 90. Going from 99 to 95 to 90, you get a smaller interval. So the question is stating, if we had made a 95 instead of the 99, we would get a smaller interval. The margin of error would be smaller because the critical value, that's the t it's talking about, decreases. As the confidence level decreases, the margin of error decreases. As the critical value decreases, they're just repeating themselves right there. Be very careful. Yours might get bigger or smaller. Double check. Explain what this means in context. Now, we're not talking about a student right here. We're talking about the average 4 students total, like the true difference between the students, not a student. So when we do this right here with 99% confidence, what does it mean that the interval here is negative? Well, the negative would be that the traditional has a higher score. That'd be the negative denotes the second mean is higher. So let's see if this works. Students in non-traditional math scores will score on average between between 3.699. So it needs to be traditional. So wait. Non-traditional will score between this much lower. Yeah, because that would mean the traditional is higher right here. There's Video Code Project 2. Yeah. We do that on the 10th and the 15th, I believe. 10th and 15th. Kale's got it down right there, 10th and 15th. And then yesterday we did it too. So we can do some more Project 2 later today. Maybe I think we have enough time. And tomorrow, check out tomorrow. So the non-traditional minus the traditional, if the difference is negative, that would mean that the traditional is higher. So with 99% confidence, students in the non-traditional math score will score on average between 3.699 lower, because that would mean that traditional is higher. So we got it right here. Good stuff. A little tricky. Negative means that the second one is higher, so traditional would be lower. Traditional would be higher, making non-traditional lower if the interval is negative. Does the result suggest that there is a difference? Now, what important value are we testing right here to see if there is a difference? It says it in the question, but to see if there is a difference, great job there, Kayla. Excellent work. When we test to see if there is a difference, what important value are we looking at? To test to see if there is a difference, there's a really important value to test. Because we're just trying to see, is there a difference right now? So what should we look at to see if it's in the interval? Which I would not reject this null hypothesis. What important value, you just need to type one thing in the chat. What important value do we need to test to see if there is a difference in the question? Like, to see if there is a difference, we'd just look to see, well, do we think the difference could be this? And it is in the interval. Not quite. So we could do a p-value. We can do a p-value to see, that would tell us statistical significance. But looking at the interval, you are on the right track. Looking at the interval, what value to see if there is a difference would you look to see, is that value? Michael, you got it right there. We're going to look to see if 0 is in the interval. So no. Let's see here. Do these suggest a difference, right? Does the result suggest a difference? No. Because the interval contains 0, there is insufficient evidence to show that there is a difference. This means we don't reject the null hypothesis. We believe that the difference could be 0 because we could test to see if the difference is 0. Great job. Is that making more sense right there, Michael? I hope that kind of clarifies. They're doing a hypothesis test kind of like you're doing on your project by looking at the interval, and they're hypothesizing that the difference is 0, and then they're not rejecting 0 because 0 is in the interval. So this is a lot like the project where we have to look at the interval and then say, well, 0 is in the interval, so maybe there is no difference. Maybe the traditional scores higher by this much, or the traditional scores higher by this much, or the non-traditional scores higher by this much. Excellent work, Michael. Great stuff right here. Got a few more questions. We'll do some 474 here soon. Let me see if I missed any other questions. Wilson's like he's always watching. That cracks me up right there. I think the 474 question might be next. Was there another one? Computer software, Michael said. There we did that question. And so I think Cora's question is next, unless I'm missing something. Wait. And then Jacob was asking about Project 2. So we could do some Project 2 if you'll want. Oh my gosh, I clicked Photoshop. So level how Brian knows what level. Yeah, I can check it. So Robert's asking. I can check it. Good question right there, Michael, asking about how can we check the points and stuff like that. It's all related to the MuBot thingy. Oh, wait. Wilson just speed ran. Okay, this. Speed run. Wilson speed ran Stat 201 right there. Wilson's doing a little Stat 201 speed run. Good stuff right there. Let's bring up the 475. Oh, crash report. That's fine. Let's head over here. Have some fun in the background right here. Okay, so 474 and assignments. My gosh. So many assignments. Let's go download the homework file. And Cora was wondering about... Oh, was Cora answering... I think Cora was also answering the... Cora, 100 points if you're still watching right now. Cora was also answering the 201 questions about 10%. Homework 8 for 474. Homework 8 for 474. Number 8. Woo, number 8. I'm looking for it. I see the tasks. Let me look at the question Cora's asking again. Put a little more chill music right here. Chill music. Doubt. So Cora said, how'd I lose it? Here we go. Hello, if you have time, can you go over the last task on homework 8? Okay, last task on homework 8. Got it. Last task. Here's task 4. The class label star dot and 2 characters x1, x2 of 300 individuals has been recorded. The data space with points encoded as their class labels is displayed. Let's go take a look at this right here. So we're going to take a look at some class labels and figure this out here. Get everything ready to go right here. Okay. So here we go. Chat on the screen. Last task. It's on homework 9. Oh, wait. So this is homework 9, right? Do I have homework 9 up? Double check it's homework 9. Is this support vector machine, right? Are you doing the support vector machine, Cora? Let's hop over to the main screen. Are you doing the support vector machine here, Cora, with the last task on the space? Okay, good. Let's make sure we're doing the right one. So let's go ahead and take a look right here. The class label stars or dot of the 2 character space in x1, x2 dimensionality of 3 individuals has been recorded. The data space with points encoded as their class labels is displayed. Would logistic regression be effective right here for making classifications? Why or why not? So what do you notice about this space right here? It's a big problem with this. How does logistic regression work? And this is great for 320. There's a big issue with this. What is the big issue with this for logistic? Like, logistic is gonna... The answer is no to this. What's the big problem with logistic right here? What does logistic need? And let's look at the logistic curve, because that kind of gives away the answer. The logistic curve has the following shape. It looks like this. Not quite good answer right there, Kayla. So the way it works is we're gonna like try to classify things, and it looks better if we do like colors of dots. And so when we do logistic regression, well, not quite linearity. What you see right here, so with logistic, it's the sigmoidal curve. So we have, that shape looks familiar. Yeah, it's sigmoidal curve. So a lot of what 320 has been covering lately. And so what do you really need to the probability of something in this space? The probability needs to have a what relationship? Think of your favorite band. Cora might know when I say think of your favorite band. The probability of something in this space needs to have a what? If there's a word you think of when you think of your favorite band, it goes in one direction. So it needs to be mono. And you don't see that for this space, for these points. One direction, monotonic right there. Yep. That's our favorite band. And we don't really see that with this data. The problem is the probability on X1 right here, you would get like, I wish I could draw on the screen. I think EpiPen is messing things up, so I'm not using it currently. But notice how the probability is like low right here, and then it jumps to like a 50%. And then if you go on the X2 dimension, great job, Kayla, right there. I think you're following along. This is kind of, notice that the probability right here is low, and then it would jump on this dimensionality. Is that making sense, Corey, right here, that we don't have... There's not a constant increase. Like, the probability on the X1 dimension is low of it being a star, and then it goes up in this dimensionality. Like, it's more likely in the middle. So there's not a constant one direction increase or decrease to the probabilities. If all the stars were over here in the corner, Logistic would probably be pretty good at it, because as you go across the dimensionality, or like the x1, x2 dimension, the probability would either increase or decrease. But the probability of it being a star is basically 0, and then it goes up higher in here. And then if you go here, it's low, and then it goes up higher in here. So yeah, just kind of put that into words, like find a good way of describing it. So we want a monotonic increase, and we don't see that. We see some sort of non-monotonic increase to the probabilities. It's kind of answering some questions. Explain why the plot indicates that a vanilla partition model. Oh, so what do we actually? So Kayla, if we're doing partition models, and I love this, what are we doing with partition models right here? Throwback to Stat 201. What are we doing with partition models right here? Because this is actually what we're doing in this class. If we're doing partition models, which I included a variable that acts like a identifier, so you don't want to do that. But if we're doing partition models, 100-point question, what are we basically doing by using partition models? And we do this in upper level classes too. If we're making a partition model, we are making what's in upper level? Decision tree, exactly. We're making a decision tree. So when you think about this right here, why do you think a decision tree would work for subsectioning this data off? If you just look at how this tree works, it can kind of slice through the x's. So this is the y variable here, but in our data, we're looking at 2 x's. So it can say below this x at this point, and it can also say above the x at this point. And so I'm kind of like giving the answer. I'm not writing it down, but we use the x's to divide the data. Now there's a y variable on this one. We're looking at different x's, but you go inside your x's and go above or below certain points, and you just keep splitting your x's, and you can just take quantitative x's and divide the data on those x's to find out the regions or the partitions. So if you look at this right here, you've got different partitions. You've got kind of a leaf here, 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 and you've got like 9 leaves by how you've cut the data. 1, 2, 3, 4. Well, I guess you got intercuts right there. You just make more x's. You're right. So here's an x you're cutting on over here. You're just splitting it apart based on this x. You're splitting it apart based on this x, and you're going above or below these values. And then this looks a little bit different because this has the y variable here, but you're just trying to put things into a group like you're doing right here and just make a leaf, like maybe this is the leaf right here where we have all of the units conforming. And you can just see right here where we're trying to get our reds and blues. So this is perfect vanilla partition, like just classical decision tree type stuff. Just by the way we can cut across the x's. There's not a monotonic increase or decrease to the data, so we can't talk about increase or decrease to probabilities. It'd be better to slice things off into groups, like totally partition data right here. Like this is, like it's literally drawn to be a partition example. And all the x's, exactly. And that's what we do. We just let the decision tree do all the work. And it's really cool, Kayla. Maybe I'll show an advanced example here to end. Optional, not graded. Oh, that would give 100% accuracy. So I'm going to leave this one so on a scratch sheet of paper. So like take a picture and add it in. Draw up a decision tree that would give 100% accuracy. Have the first rule be this right here. So draw that in on your rule. Have the first rule be this. Yeah, so I'll let people draw that out. I won't do the bonus right here. But I'd like to show this. What we can do right here is we can actually make our own. You're welcome, Cora. Thank you so much, Cora. We've got open floor questions. So what I'm going to do right here is I'm actually going to use some stat tool on data. Do I have survey 10 loaded up? So Kayla, this is kind of a peek into the future of how we do more advanced things. And we're going to load up survey 10 right here. And so we should be able to make a tree pretty quickly with our R part. Try to do this from memory right here. Boop, 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 boop. It's good practice. Let's go here and I'm not going to do, so 474. And Brian is not doing validation / holdout. This is just a decision tree example. So I'm just doing descriptive analytics. I'm not doing predictive analytics. Descriptive analytics being used. So I'm not doing any predictive analytics, so I can't get holdouts. I'm just doing descriptive analytics. So let's go here. I am going to use the train function here. Let's go to tree. Should be able to get it via the R part. So we can go to train. Oh, we don't have caret loaded up. libraries, caret, got so many. And we're going to go here and predict somebody's gender. And we're going to use height. No, because we'll eventually see that probably. He's and then we're going to go y tilde x comma data equals 320 and 474 should know that quite well. Y tilde x comma data equals comma method equals r part. And we don't need even a preproc. We might be fine on this. Error possibility. I think it's mad about one of the variables. We'll take a look here at the variables that we got. Let's try running it with columns 1 through 5. Oh, it's mad about something. Name. Oh, my gosh. There we go. There we go. So now we should have our tree. It should have created it. And so that's the code we need. I think we've got this. Doing it all from memory right now. Fancy. Oh, we need to go to library rattle. Libraries are kind of what give you your functions. So if you see me loading a library, it's because I want to do what's called a fancy R plot. And let's see how crazy our tree looks. Oh, it doesn't like it. There's our tree. Do we have to run the R part on it? We have to actually run R part on this. Predicted, dots, metric, control, final model. Might have to actually look at the final model on this. There we go. Here is our tree that we created to predict if somebody is male or female. And it does pretty well. The best way to the best conforming leaves, the ones with the best entropy, Gini, all that good stuff right there that we've been talking about, would be these leaves right here where we have pretty much all males with 43% of the data down here. And this is only 1%. And this is the majority female leaf. So the people who are mostly female, and just take a look at this, the number one question to ask somebody if they're male or female would be what? You ask them this question and then you basically, it kind of decides it. So it's not that they will be this, but if you ask somebody this question, then you have a really good indication if they're male or female. It's pretty crazy. You just say, how many what's? The number one thing, this is an X variable you're cutting on right here. So this is StatTool1 decision trees with 474 also. So, and this is a much more advanced way of doing it. We can just do any sort of variable on. What is the number one thing you could ask somebody? How many body piercings? And they're like, I have 3 body piercings. Say, okay, you are probably female. Very highly likely someone's female if they have more than 1.5 body piercings. 1.5 is not the amount of body piercings you can have. This splits people apart to the people who have 1 or less body piercings or 2 or more. Like everyone over here must have 2 or more body piercings, and having 2 or more body piercings is 54% of our data, and the probability of you being female then is 97%. If you only have 0 or 1, which I would fall into, we'd then ask you, how much do you want to weigh? And I would say, do you want to weigh less than 137? I'd say, no, I want to weigh like 175, 180. So I'd go over here and I have a 99% probability of being male. 43% of the people in the survey answered the questions the way I did. But if you say, yeah, I want to weigh less than 137, we say, okay. How funny do you think you are? So weird that we get this. But then the question becomes, how funny do you think you are? And we say, do you think you're funny? Then less than 63% of people. So weird. Now, this is a very small subset of the data, but males do think they're funnier, apparently. Because of the tilde, does it mean does not equals? So the way the tilde works, it's the formula format. So that says create a formula, kind of like when you see the y tilde right here in code. This means like y is gender. So gender equals some formula of the x's. That's all the x's right there. The dot stands for all the x's. And this is code for the formula format. So if you wanted to create a plot right here where you plotted height tilde weight, this should work. So what is going to go on my y-axis when I look at this? When I create this, and I think this will work with base R functions, what would be on the... You're hilarious. There you go. From the philosophy says, oh, no, we use it for the formula format. So what would go on the y-axis when I run this plot right here? When I create a plot of this right here, what would go on the y-axis? What would go on the y-axis? The y-axis is going to have what variable on it? If you look at the format of it with... Oh, using like not? Oh, yeah, they do use that. They use like not p, like tilde p. Height. Kayla, great. Yeah. Kayla, you're getting ready for some 320 right here, because this just means a formula of the y and the x, where we're doing like y equals some formula of weight. So if you're understanding this right here, y tilde x comma data equals the first argument. So there's a little 320 review right here. Every time we do a new argument, what separates out new arguments? So every time we separate out a new argument, we must put a what? And I'll make this look a little bit nicer right here. If I want to put in a new argument, I must add a what? Which arguments are instructions? So the instruction for the formula is height tilde weight. That's the formula instruction. The instruction for the data it's using is survey 10. If I want to put in another argument, I'd put in a what? Oh, you got it. Yeah, proofs. Oh, man. Tilde P, not P, all that's good stuff. P, not P. That's a bit of a problem. Another argument, we must just put in a what? One button to press it. If I want to put another argument right here, I'd do what? A little bit of 320R help right here. And if you have a question, put it in the chat. So look at every time I put in a new argument, I'll separate out my arguments. So you got it, Kayla. That means new instructions are about to be given. Those instructions just ended, new instructions, and you can hit enter to start a new line to make it look nice and neat. The argument main is, or is it not? Yeah, it is. What do you think main changes right here? Great job, Kayla and Sophie, 100 points. What do you think main is controlling right here? What do you think main is doing? You notice I did something a little bit interesting for this. Main is the what, it's controlling the what for this plot. Main is controlling the what. Like the argument main is controlling the what for this plot. And it's called main. That's the argument name for it. So it's saying main is like, okay, put this as the what for this plot. And the reason I'll say this while people are thinking this over, the reason I put it in quotes is because it's words. If I don't put it in quotes, it'll think it's an object and it'll say hello cannot be found. If I put it in quotes, it looks at it as words. It's the title exactly. So this right here is an object. It's a data frame, and this is a vector inside the data frame. That we're going a little bit too advanced by saying that. Just remember that if things are in quotes, does that make sense that these are words? Like if you put things in quotes, those are words. This is like, we're just talking some basic, like some just, if you see something in quotes, like if I do paste, let's do this. Here's a good example. Let's say, hello. Let me ask you this question. How many arguments are in the above function? How many arguments are in the above function? So, also familiarized with log regression, is it basically? Logistic regression does nonlinear. Logistic regression does nonlinear if it's a nonlinear curve. I can show some of that here too. Good question, Sophie. And ask all your advanced questions. We're just chilling out right here. How many arguments are in the above function? Right here, this function right here. How many arguments are in it? Arguments are always separated by commas. Arguments are just different sets of instructions, and this is pasting things together. I'm not trying to write any trick questions right here. So how many arguments are there? So 5. Good guess there, Knox. I'll take a guess of 5. That's a guess. Good guess there. Good guess, Knox. Not 5. If you have a question, 201, 320, 474, 475. It's an exponential regression that is linear, right? Kind of, sort of. And Kale, you are right for another 100 points. There are 2 arguments. There are 2, and logistic is nonlinear. Correct. There's 2 arguments. There's this one and this one. Now be careful. What will this paste? When I paste this, what will it show me? Paste is going to put them together into one thing. What is this going to say? Hello, Brian? What will it say right here? And this helps indicate why it won't say hello, Brian. What's it going to say? You can cheat and look up here. What's it going to say when I run this code which pastes these 2 things together into one kind of sentence? So paste is going to put the things together. It will say hello, and then it's going to say hello what after that? It's not going to say hello, Brian. It's going to say hello what? It's going to say hello what? It's going to say hello. Yeah, let's do a serial question next. Here, we'll do that in 1 minute here. Thank you so much, Caroline. We'll do that next. Great question. It's going to say hello what? You got it, Kayla. I know you got this. It's not going to say hello, Brian. It's going to say hello 5, and there'll actually be a space. So there'll be a space right there, which you might not have known. Very good, Kayla. Don't worry. You would not have known the space. That's the default separation because right now Brian is 5. Does that make sense right there? Brian is 5. So if I change this to like, let's say Darren, it's actually going to say hello, Darren. Even though we're saying paste hello, the object Brian, we could change it to world. And now it says hello world. Because Brian the object Brian is the word world. So the object Brian, because Brian exists as a value in the brain of R up here, and the object Brian is the word, and you see how it's in quotes, world. So it says hello world. And the comma is the comma is not the space. What it is there's an argument sep, which has a default of a space. But if I change the argument sep, which tells it how to separate out each of the arguments, to this, now you see how it says hello world with no spaces, but the argument sep controls the separation between each argument. So if you just add something like this, you get that. And that controls what is separated. And by default, it's this right here. Like that is the default if we don't make any changes to it. Yeah, no, these are the great questions. So the comma isn't the space. It's just that the default between each argument is sep. And let me say one last thing. We're going to do Caroline's question. If you were ever wondering about these things, you can actually look at the help function and you see how they say here sep equals this. So if you do not enter anything for the separation, it'll do this right here for you. And it's actually telling you the other arguments being used, like collapse equals null, recycle equals false. I don't even know what collapse and recycle does, but these are the default values if we don't change anything. And the argument paste 0 actually has the default separation of no separation. So if you do paste 0 like Brian, comma Darren, you don't have any ability to separate them now. Now paste 0 does no separation and you get the following. So great stuff right there. Really good questions. Just understanding how R works and the terminology of like arguments, objects, words, which we call strings. And this is just some practice here. Just hearing it a little bit helps out. Let's hop back to the main screen. Caroline, thank you so much. Our new music today. We're just going to play the heck out of it. Knox, great to see you here. Ask those questions. We're going to do Caroline's question about the cereal question. Neighbors are like, he's teaching again. He's yelling about some questions. We always joke that our neighbors will like know statistics. They like sleep during the day or something, and they just hear me like teaching statistics in the background. And they wake up and they're like, QQ straight enough, no outliers, plot doesn't thicken. How do I know all this? How do I know these statistical terms? They like subliminally are learning statistics. So for this serial, no serial question, make sure to have Jump ready to go right here. Let's go check out Jump. Serial, no serial question. Let's do this. So this is the serial for adults or children. And just go with what you know. Children's cereal has more sugar in it. We already know that. We already know. It's the best cereal out there. Some Lucky Charms, some Trix, some Fruit Loops, some Rice Krispie Treat cereal. That stuff's like candy. It's good. We've got our data right here showing us that the children's cereal has 43.4 grams of sugar and the adult cereal, 0.5 grams. That's got no sugar in it. Probably good for you, but we don't want none of that. So we're going to go here and copy the data first. So we're going to copy to the clipboard. Pausing right here. And then we're going to take this data and hit Control or Command C. A few times. Works better. And then hit Done after copying the data. Now you're going to go over to Jump, and you can be anywhere inside of Jump, preferably probably be in a data sheet. And on a Mac, you'll go to the top of the screen. On a PC, ooh, Kix is good too. Kix is very good. That's been around for a long time. Little tiny puffs right there. Go here to File, New Data Table. I think I did nonlinear regression in pre-calc. That's why it's, yeah. So go to File, New Data Table. Under File, New Data Table, make sure, don't click inside of it. Don't click inside of it. Go here to Edit, Paste with Column Names. Edit, Paste with Column Names. Just put it all on the screen one time right here. Edit, Paste with Column Names. Yep. That's logistic. You totally were doing it. Edit, Paste with Column Names, and you see the column names goes at the top. If it looks red, you've done it wrong. So if it looks red, you need to restart. Make sure to paste with column names. Don't click inside of it. And you should be good to go. Just make sure to paste with column names. So now that we have both serials in here, we can see the same data we were looking at previously. We're going to go here to Tables. And under Tables, we're going to go to Stack. That's Tables, Stack. And with Tables, Stack, double-click both of them. After double-clicking both of them, you will see children and adult cereal in here, and we're going to click OK. And now we have the data stacked, so we have a two-level categorical variable, and we have a just data right here with the cereals. You can kind of see the shape of it. We got a little bit of bimodality in here, probably from the data itself. So make sure you have the 2-level categorical, which means we can do the 2-sample t-test. And we have here the data is a quantitative y variable. Review the steps if you don't see red and blue with your labels and your data being the following. From here, we can go to Analyze Fit Y by X. Pause right here, make sure everyone's on Analyze Fit Y by X. And we click it. Doop. And now we're going to put inside of here, the data goes inside the y variable, which is what we're analyzing. We're going to analyze a quantitative y for the 2-sample t-test. And the label right here is a categorical 2-level x. So we're analyzing a 2-level categorical x for the 2-sample t-test. Quantitative means it's a t-test, and 2-sample means it's 2-level categorical x. We go ahead and click OK, and we see the output. Pretty obvious to tell at this point that children's cereal has more sugar than adult cereal when you look at the distribution, because this is the highest adult cereal, this is the lowest children's cereal in grams of sugar. To do the 2-sample t-test, we can click over here to the t-test under the red arrow, and this will do the 2-sample t-test for us. And we get the following output. I'm going to make this a little bit smaller so we can get it all on the screen at the same time. Here is the 2-sample t-test, and we get a confidence interval. I am 95% confident the true difference between the children's and adult cereal sugar content is contained in the interval 31.73 to 39.97, and that does not contain 0, so there's definitely a difference. Like, this is, children's cereal has way more sugar in it. We probably didn't need to run a statistical test to do that. We probably just needed to eat a bowl of cereal of each and be like, yeah, well, that'd be a sample of 1, so maybe we should be doing statistics and not taking a convenience sample of 1. So we do see strong evidence right here with our probably random sample collected from less than 10% of the data with what actually looks to be mostly normal. If you wanted to check to see if it's nearly normal, you could put some border histograms on this and take a look. So you want to go here to the display options, and we could look at the border histograms, and they're skewed, aren't they? Might just be the size of the scale on it. Are they skewed? I don't know. Sample size is kind of large. Got like 30 from each or so. Something like that. Maybe 20, 25 from each. One of them has less, I think. What is the T ratio? Great question right there, Knox. What is the T ratio? The T ratio is the standardized difference. And so how would we get this T ratio on this screen? So Knox asked such a good question right there. The T ratio is the difference divided by the standard error. So to get the T ratio, we would do the following formula. Knox, can you solve for me the formula for the T ratio right here? Can you take the difference and your standard error and get the great job right there, Kayla. Chapter 17 homework? Yeah, Memu Nunusi. Yeah, we got just enough time. Let's do that here next. So how would we do this? I'll probably send out the announcement to the afternoon class, telling them class starting in soon. So how would we find that T ratio? Kayla put the formula in the chat. So be like, okay, if we don't have the T ratio, how could I solve it using the numbers right here? Because we have the difference between the two means. That's what this is showing us, that children's cereal minus adult cereal has a difference of 35.85. And that shows us good evidence that children's cereal has more sugar than adult cereal because the interval down here does not contain 0. We think that children's cereal has somewhere between 31 to 39 or 32 to about 40 grams more sugar. And we see here the standard error. The difference is this. So how could you get the T ratio? Mathematically, Kayla's put the formula in the chat. What is the mathematics for this? And Kayla, I want to point something out. You might notice this, Kayla. Do you see how the standard error is 2? The T statistic would be about 2 for the confidence interval, and that's why the margin of error down here is 4. Just a quick kind of aside. The margin of error here is very close to 4 because you basically have 2 times 2. The T for the confidence interval, which is not this T. This T, and we talked about this earlier, is not the confidence interval T. This T you see right here is the T being used for the standardized difference, and the formula for this T right here would be, let's show it, to get that T, it would be the difference of 35.85, and there's the difference, divided by the standard error of the difference, and that gets the value right there if we round the decimals. Does that make sense right there, Knox? To get the T ratio, which is the standardized difference, and that's not the T for the confidence interval. The T for the confidence interval would be looked up via the app, and you get to pick it based on the percent confidence, and this is not the T for the confidence interval. That's probably one of the biggest confusions. T for the confidence interval has T star. This is just the T solved for the standardized difference. And so 31.73. Awesome, Knox. Great job. 100 points right there. Keep it up. Keep asking those questions. We'll try to explain everything we can. 31.73. 31.73. And the other interval is 39.97. Hopefully I copied these correctly. Adult cereal weight with 95% common children's cereal average between lower bound more grams of sugar. There's the upper. There's the lower. And let's double check. 39.97, 31. And moving to a new city right here. So let me hop back to the main screen. Time for a man moving to a new city. Time to solve some equations. Great questions. Shivram right there. Excellent work. A man moving to a new city. You got just enough time. I'm going to send an announcement to the class real quick for the afternoon. Remind them that we have class coming up right here. Class coming up. Afternoon class. Link about to be sent out. Oh my gosh. I cannot believe it. We are in the home stretch right here. People are in the chat saying, hey, everyone. There we go. And let's go here to announcements. Plus class in 27 minutes. Big bonus. See you soon. Suno. Click here. Okay, link is good to go. Sending to the right class, right? I think so. Let me look at the announcements. Good. Right class. Okay. It's like, what if I send to the morning class again, the afternoon class? Like, I never got the link. Awesome. We're good to go. Office hours. Got 11 people watching. Thank you so much, everyone watching right now. Here we go with a man moves to a new city. Let's go check this out. So we need to create a 95% confidence interval for the difference between the route times. So he's going to measure the difference between B minus A. Now that's usually where the mistake happens. We're doing the difference between B minus A. So be very careful right here when you're solving this. So let's grab the data. Remember, it's 95% confidence for B minus A. And so now what we need to do is we need to do what? Just tell me what I need to do and I will do it. I might actually start doing it in the background here while you say, Brian, you should do this whenever you get a question that you have to solve a formula for. If you are going to solve a formula-based question, you probably need to. That's weird. It's got so many, I think the updated word. Probably we need to do this. We probably need to do this. What do you think we need to do? Which I'm starting to do right now by writing out this, but then I'm going to need to find all these. And make sure you know what these are, because it really comes down to solving these questions by knowing the notation. So I'm writing down the formula I'm going to use, and then I'll need to identify all of the notation. And wow, what am I doing right there? That was weird. Nope. Okay, there we go. You might say, why is it B minus A? It's just the way they wrote the question. And I did forget my bars on top of my Y's, meaning the mean of Y. I was saying the individual. Without the bar, it means the individual value of Y, but with the bar, it means the mean of the Y. So everything should be correct right here, right now. And now we just need to identify. Let's go through here and start seeing he rides each route which amount of times. He's going to ride each route 20 days. Driving each route 20 days, that means that's the sample size for each route. He drives each route 20 days. That is the sample size for each route. We have here the mean for route B. Route A takes 45 minutes. I just saw that one first. It's up there. Route A takes 45 minutes. And route B takes 46 minutes. That's a 1 minute difference. We're probably not going to find significance. We could. You never know. Now we need to go here and take the standard deviations. The standard deviation for A is going to be 5 minutes. That just says up there the standard deviation for A, which is route A right here, is 5 minutes. And that's squared. Don't forget to square it. That'll cause the wrong answer if you don't. And the standard deviation for B is 2 minutes. So that's 29 over 20 square root. I don't know that in my head. Okay. And the answer is 5. Oh, you're talking about, yeah, great job right there, Knox. Thank you, Knox. You're probably talking about the standard deviation right there. I appreciate that. So this is, we're doing the difference, but now we need one more thing, and this is where people usually get stuck, is we need the t with the degrees of freedom. We have to first find out what the degrees of freedom are, which tell us which t distribution we are using. So the degrees of freedom right here are a complicated formula, and we will not ask you to do this on the test. You have to use the standard deviations and the sample sizes right here and go to the t-applet and put in your sample sizes of 20 for each group, your standard deviation of 2 and 5, and then you get the degrees of freedom. We're going to round this up to 25 when we put it into the applet, because now we need to go over here after getting the degrees of freedom and take this, because this tells us which t we are using. So all I did was take my information, sample size 1, sample size 2, standard deviation 1, standard deviation 2. I take this information right here. I'm going to see if it changes it when I do it. And go to my t-applet and drop it in for the degrees of freedom. All I'm doing is taking that and put it right there. Let me see if I put it to 25, 2.064. See, I think... I'm going to put it to 25. I'm rounding it up. I would round it. This applet doesn't do decimals as well. I would round it right there, at least in this instance. I'd round up or down just to get, because it's a decimal degrees of freedom and this applet doesn't do decimals. So I would take the rounded version. Just tips right there on doing this question. This is the t-score on a t with 25 degrees of freedom, which is basically what we see here. So it's 2.06. And 2.06 is what's going to be applied here. Now, what do you notice about this? We're making a 95% confidence interval, and this t-score is very close to what? Now, it's not quite this, but 68.95, the t-score is very close to 2. Now, it's not quite 2, but the t is like the z. It's like the z. Depending on the degrees of freedom, the t will change, and it's important to know we have a 95% confidence interval because 5% on the outside. Might make more sense to see it this way with 95% on the inside, but if the t had less degrees of freedom, it would be very different. The lower the degrees of freedom, the more different the t is than the z. The more degrees of freedom you have, the more it'll be like a z, which is 1.96. Very important right there to make sure to find your t statistic based on your degrees of freedom using the applet right here for the degrees of freedom for the 2 sample t right there. And links are in the chat. Okay, so now that we have this right here, we just need to solve the equation. That is 29 over 20 square root. So 29 over 21.45, square root of that, can't do that one in my head, 1.204. And that is this number here. We multiply this by 2.06 to get the margin of error, 2.48. So the first part of the equation is 1, because it's 46 minus that, plus or minus 2.408. Just solve through the equation. This is the estimate of the difference. And then this right here is the margin of error of the difference. So we would create the interval. It's going to go negative. So watch out right here. I think it's just going to be negative, yeah. Do we have faculty meeting today? Well, I can't show up to that on time. I'm teaching. Negative 1.408 to 3.408. And that is the interval right there to estimate the differences. 1 minus this. There we go. I don't think we need to go to that many decimals. 4.80. That's how errors occur. That's how errors occur. And we just add and subtract the numbers right there. Add and subtract. So that will give us the numbers right there of 1.408 and positive 3.408. So negative 1.408 to positive 3.408. So negative 1.4080. I keep reversing it. And 3.480. Let me look at that number again. Yeah, should be right. How many decimals? 2 decimals. Boop. Boop. Double check those decimals. So the man, should we believe the 5-minute claim? No. Because 5 minutes is not in the route. Looks like we'll save somewhere between negative 1.48 minutes, 3.48 minutes. So it could be that route A takes longer. It could be route B takes longer. We do not have 5 minutes in our interval. Your interval might contain it. Woo, got a little bit scared that last question. We've gotten perfect today. That's how we try to run here. But Shivam, I hope this helps out. That's got it today. That's the last question here. Great work. We'll be teaching here in 19 minutes. So swing by class, practice up. I'll see everyone soon. Bye for now. Bye.